Hello? Okay, perfect. Alrighty then. Well, hello everybody, and good evening. Thank you all for coming. So today, the story I'm going to be telling is going to be a little bit more different than what my fellow classmates have presented so far. I will be talking about weather, specifically about uncovering the secrets growing inside of winter storms. But before I get into that, first, let me just talk about the weather more generally. So, have you ever checked the weather app on your phone and you're like, oh, no way, it's going to be sunny outside? Oh, yes. And then you imagine this picturesque view of Seattle with not a single cloud in the sky. It's all sunshines and rainbows. But then you go outside and you see this. Cold, dark, dreary, rainy, and depressing. Gosh, what a letdown. So, evidently, weather forecasts are not always perfect. And unfortunately, this is especially the case when it comes to snowstorms. So sometimes forecasts say that it will only snow an inch, but when folks go outside, they see a foot of snow or more piled up in their driveways. So while we may not experience this kind of weather here in Seattle, it is very common in the Midwest and the Northeast during the winter season. Now, why do forecasts struggle to predict snow? Well, this is because forecasts take shortcuts in how they represent certain parts of snowstorms. So, assuming many different things about their structure, their size, etc. And one of the rather bold assumptions that forecasts make is that all snowflakes inside of winter storms are shaped like this, round ice balls. And so forecasts do this because it is easier and allows them to make faster predictions. But really, at what cost? Because in reality, snowflakes are not all round ice balls. They actually come in a variety of different sizes and shapes. So what you're seeing here are just a couple pictures of what snowflakes look like in real live snowstorms. So clearly, none of these look like round ice balls. So looking at these pictures, I'm sure a lot of you might not be familiar with some of these snowflakes. And when I said the word snowflake, you probably all imagined this six-sided branch snowflake seen in most cartoons. Well, this is actually this guy. So the iconic six-sided branch snowflake is actually called a dendrite. And although I didn't show it in my previous slides, dendrites can actually grow quite large. And that is because of their branches, which allows them to clump together really easily in order to create even larger snowflakes. So this clumping together is a process called aggregation. Oh, kind of broke off there. But yeah, aggregation. And it is believed that aggregation plays an important role in causing heavy snowfall. So this is one of the reasons why scientists think, big emphasis on think, that dendritic growth inside of snowstorms plays a role in producing the heavy snowfall that, one, forecasts struggle to predict, and that, two, has major societal impacts for us on the ground. Now, just imagine if dendrites were to highly affect snowfall, just how problematic it would be if weather forecasts knew absolutely nothing about dendrites. Well, I hate to break it to you all, but fortunately, forecasts don't know anything about dendrites and how they grow in snowstorms because, again, they assume that all snowflakes are round ice balls. So, if we want to improve our forecasts, then it is a good idea to first understand the role that dendrites and other snowflakes play in snowstorms. All right, so with that, where do dendrites grow? Well, Studies growing snowflakes in a lab have seen that dendrites grow between the -4 to 14 degree Fahrenheit temperature range in extremely moist air. And so that -4 to 14 degree temperature range in snowstorms is actually a cloud layer that sits at about 15,000 feet or 4.5 kilometers above ground level. So for reference, the top of Mount Rainier, the summit of Mount Rainier, is about 14,400 feet tall. So our cloud layer of interest sits just a little bit above the top of Mount Rainier. Okay, so with that, what does this cloud layer look like inside of a real snowstorm? Okay, so what I'm showing you guys here is a radar image of what a snowstorm looks like from its side. And so essentially what you're looking at, these are all clouds, and these clouds are extending upwards towards the sky, resembling towers, okay? So essentially how a radar works is it sends pulses of energy out to the storm. And those pulses of energy, they come into contact with the clouds and with snowflakes, and they bounce off of the storm and come back to the radar. So the power of that return signal is referred to as reflectivity. And so really the important part that I want you to know about reflectivity is that high values of it exceeding 20, so in this case the yellows, the reds, the pinks and purple colors, that means that there's enhanced precipitation or that there are large and or more particles growing. And so highlighting where our cloud layer sits in this snowstorm, you'll see that it actually sits in the upper half of this picture. And we can see right away within this cloud layer that there are pockets of high reflectivity where there's these brighter, warmer colors. Well, actually, yeah, so 15,000 feet above ground is also where bright signatures in radar images are often found inside of snowstorms. So scientists seeing this were absolutely perplexed. They were like, God, what on earth is causing these signatures, right? And so they sat back and they rubbed their chins and they're like, okay, well, if high reflectivity means that there are larger particles growing, what large snowflake grows between this temperature range? Oh yes, lab studies said that dendrites do, so you know what? Yeah, I think it's probably, these signatures are probably just dendrites growing, probably. So yeah, scientists were quick to blame these bright signatures 15,000 feet above ground on the growth of dendrites. And so this cloud layer, 15,000 feet above ground level, was given the name of the dendritic growth zone. But the truth is, scientists don't know for sure what is growing in this cloud layer. So are dendrites really responsible for producing heavy snowfall in this cloud layer? Is this layer really the dendritic growth zone? I mean, because sure, dendrites have been grown in a lab, but we have never actually observed them in a real live snowstorm 15,000 feet above ground. So the only way to find out was to fly directly through snowstorms. And so that is where my research comes in. So basically, I am part of a NASA-funded field campaign that involves flying these two aircraft through snowstorms over the Midwest and the Northeast in order to scan and sample the snowstorms. So essentially what you're looking at here, the top aircraft is the ER-2. So the ER-2 carries on board all of the radar instruments. And then the bottom plane right here is the P-3, which has mounted on its wings all of the instruments necessary to sample the clouds and the snowflakes. All right, but when I say sample the clouds and the snowflakes, what do I even mean by that? What does that even look like? Well, in a nutshell, we shoot lasers at snowflakes to take pictures of them. So Here are a couple examples of what that looks like. So one instrument mounted on the plane, this little guy right here, essentially shoots lasers, two lasers in an X pattern, such that whenever a snowflake flies through the crosshairs, silhouettes of their shapes are imaged instantly. And so we're very familiar at this point with what a dendrite looks like. And as you can see, their branch shape makes it very easy to identify dendrites in these type of pictures. But this isn't even my most favorite instrument. My favorite instrument is this one right to the left. So this instrument, inside of it are two cameras, a mirror, a flashlight, and a laser. So essentially how this instrument works is this laser basically remains on at all times, and it's there to detect when a snowflake flies into the instrument. And as soon as it does, a flash goes off, it bounces off of the mirror and into the two cameras, and the snowflake is imaged instantly. And so the result is a crystal clear image of a snowflake. So what you're looking at here is a snowflake that was imaged by this instrument during one of our flights. So it's pretty neat. So speaking of flying in the P3 and all that fun stuff, fun fact, I actually got to fly in the P3 while we were sampling the storms. So here are just a couple pictures that I took while I was out in the field. So the picture to the bottom left is what the P3 really looks like. And to the right is what the P3 looks like from the inside. So it looks pretty gutted and sad in this picture, and that was because at the time, NASA was replacing the insulation in the plane. So unfortunately, it meant that during our flights, we had no insulation in the plane, and it got really cold. So we were asked to bundle up with several layers because, we're flying up in those snowstorms, it gets pretty cold. Anyway, so these flights lasted anywhere between 6 and 8 hours, so they were quite long, but I promise you that when you're there and you're busy and you're taking notes and keeping track of what's going on, the time flies by super quickly. So, okay. So, in a nutshell, in summary, the ER2 and the P3 flew together in order to scan and sample the clouds and snowflakes 15,000 feet above ground. So what this looks like is essentially the ER2 actually flies above the P3 and above the snowstorm itself in order to scan the storm from above. So you'll notice that the radar beams are actually pointed downwards towards the ground at all times during the sampling. Whereas it's the P3 that actually flies directly through the storm within our cloud layer in order to do the sampling. Okay, so now what you're looking at is another radar image. This time it's a bird's eye view looking down at a storm that occurred over Portland, Maine on January 23rd, 2023. So what I'm actually going to show you guys shortly is a video of what this coordinated sampling looked like between the two planes. So for context, the ER2 is going to be represented as a blue dot flying from Dobbins, Georgia, while the P3 is going to be represented as a black dot flying from Wallops, Virginia. So as soon as I play the video, you're going to see these two planes fly towards the storm over Portland, Maine, make some sampling along and across the storm before returning back to base. All right, so there we go. The planes are flying towards Portland, Maine, and as soon as they're together, they start making in-sync sampling along the storm and across the storm before flying back to base. So one more time. Two planes, they're together, they fly along the storm and across it before returning back to base. All right, so now what you're looking at is a picture of that same exact storm viewed from its side, taken by radar on board the ER2. So this pink line represents the flight track of the P3, so you can see where we flew within the storm as well. And so highlighting the dendritic growth zone, we'll see that the P3 actually flew in the cooler end of the cloud layer this time. And we can see evidently that there are pockets of high reflectivity within this cloud layer. And so this suggests that there is enhanced snowfall occurring with larger and or more particles growing. So, if scientists have been right or have been correct about their assumptions, then we would expect the P3 to have observed dendrites flying through this cloud layer. So, did the P3 see dendrites? Yes, the P3 imaged dendrites while flying through the storm. And so these are just a couple of pictures of what these dendrites look like, but that was not the only snowflake type that was imaged. So we saw other familiar looking snowflakes like plates and capped columns, but mainly what we saw were actually a lot of these misshapen looking snowflakes, basically polycrystals in the mix. And so this is significant since these misshapen snowflakes, we don't really necessarily think of them to enhance snowfall. And that's just because, for example, they don't aggregate easily, they don't clump together. So this was definitely interesting to observe. And this suggests that maybe there are more to these misshapen looking polycrystals than meets the eye. It is also worth noting that the bright radar signatures are not always seen within the dendritic growth zone. So what I'm showing this time is another side view of a different storm, this time over the Midwest on February 14th, 2023. And highlighting the cloud layers in dendritic growth zone, we can see that there are no little pockets of high reflectivity within this cloud layer. So with that, what did the P3 see? Did they see any dendrites in this cloud layer? No, little to no at least. Literally only just one dendrite was imaged throughout this storm. Instead, we saw a lot of different types of snowflakes. We saw these guys. These are actually called bullet rosettes. And so like the name suggests, bullet rosettes basically look like bullets with their tips joined together at the edges, and so hence the name bullet rosettes. And these snowflakes typically form in much cooler temperatures, much higher up in the storm. So what we think happened here is that these snowflakes probably formed higher up near cloud top, and they fell into this cloud layer, into the dendritic growth zone, and the P3 probably just imaged them. So nothing really, groundbreaking about this. But anyway, yeah. But what we can say, though, from looking at these two storms is that clearly our understanding of snowflake growth 15,000 feet above ground is not as good as we thought. Because number one, the bright radar signatures in radar images are not always observed like we originally thought they would be. And number two, when we do see bright signatures and we do happen to see dendrites aren't even the dominant snowflake type that we see. In fact, these dendrites are surrounded by these misshapen-looking polycrystals. So essentially, this is important to us because if we are mostly seeing snowflakes that aren't dendrites within pockets of high reflectivity, then maybe this means that dendrites alone aren't to blame for enhanced snowfall. And perhaps the dendritic growth zone is a lie. And so that's one thing. And we care about this piece of information because when we are hoping to improve our forecasts, we've been thinking all along that we need to start representing our snowflakes to look like dendrites, right, instead of round ice balls. But maybe that's not actually the case. Maybe we need to be representing our snowflakes to look more like polycrystals as opposed to dendrites, right? So all these little minute details is really important when it comes to trying to improve the accuracy of our weather forecasts. So I want to emphasize that fact. But, conclusions like this, that's a really bold conclusion, a big conclusion to make, and we can't make it quite yet until we have more analysis, looking at more storms to see if we see these patterns across multiple other cases instead. So more analysis is needed in order to reach a final verdict. So until then, dendrites continue to remain front and center of this investigation, but the scientific search for answers is far from over. Thank you.